Okay, so I'd like to finish up a little bit of the necessary background before we get to some examples of hypothesis testing. So we looked at a whole bunch of things before break about how do we get started looking at what is the null hypothesis, what is the alternative hypothesis. Based off of that, we did some other things about type 1, type 2 errors and things. And so now we're going to take a look at one of the last ideas that we'll need to fully understand. Okay, so definition here. So the definition of a p-value. So the p-value, this is going to be the probability that if the null hypothesis is true. So remember, the null hypothesis, this usually says that nothing is different. This is the one that you can always use an equal sign if you want. So maybe you're saying mu is equal to 80, or you're saying that a proportion is going to be equal to 0.5 or something. I don't know. So we're basically saying that we just assume that if the null hypothesis is true, okay? So it's probable that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. Okay, so this is one of the trickiest definitions that we're going to work with in this class. This is one where even professional statisticians sometimes try to say something that isn't true about a p-value. So the main idea is this is the probability that you get a result that is as extreme or more extreme than the one we got on our sample. Because remember, with hypothesis testing, we're taking information from a sample and we're trying to generalize it about some claim dealing with the population. So if you were to get a sample that is ridiculously far away from what the population mean we might expect to be, what the null hypothesis would say it is, then that's a really extreme value. But let's say, for instance, our null hypothesis says that the mean is equal to 80, and we got a value that was 80.1. Right, so let's say if the alternative hypothesis says that it's larger than 80, well, to be as extreme or more extreme, that would be something that is larger or the same as 80.1. So if we were to repeat this experiment again, what is the probability, just due to random chance, that we have a data value that is further away or the same as what our current sample data was? That's a p-value. So alpha, this is something that we introduced just at the end of the last class. So alpha, this is the probability of a type 1 error. So if you look back, remember we had a type 1 error, we had a type 2 error. We said that those two occurred when either if we rejected the null hypothesis but it was actually true, or we did not reject the null hypothesis when the null hypothesis was false. Right, so those are the two times we might get an error. A type 1 error, that was the choice that when we reject the null hypothesis, but it's actually true. So remember, if the null hypothesis is actually true, then what that means is that there is no difference, that there is nothing going on that's different than what we assume is true about the population. So if we reject it, we think there's something different, but in reality, there isn't anything different. That the only reason there's difference is just due to random chance from sampling error. Okay, so that's alpha. So when it comes to one of the last steps in hypothesis testing, we're going to be calculating p-values. We're going to be working with alpha values. The last thing we need to do is we need to determine if we decide to reject or we do not reject the null hypothesis. Remember, hypothesis testing, we are testing claims. We're trying to evaluate, is a claim going to be seemingly true or false? So we need to have some decision. Either we are going to say, I reject the null hypothesis, or I'm going to say, I do not reject the null hypothesis. An important note is we will never, ever, ever say that we accept the null hypothesis, right? So we either reject it or we do not reject it. You might be thinking, well, if I don't reject it, that means I accept it. Not quite. So when we work through some examples, we'll see kind of verbiage-wise, why are they slightly different things? Because remember, if we accept the null hypothesis, that means that we have to know something about the full population, and we don't. Right, we only know things about the sample, and so we just know something about a small group. We can't know everything about the large population, so we can't ever accept the null hypothesis and say, yes, that is absolutely true. Okay, so when we make this decision of whether or not we reject or we do not reject the null hypothesis, what we're going to have to do is we're going to compare the p-values. Remember, this p-value, however we get this, this is going to be compared to alpha. So remember, this is also the alpha, the same type 1 error. Now, the name that this often gets is the level of significance. So I might be saying at alpha equals 0.05 level of significance. So remember, if alpha equals 0.05, that's the probability of a type 1 error. So we don't want type 1 errors to occur. So alpha is usually going to be a pretty small number. It's going to be something that you'll be given into the problem because this is the level that we can be somewhat confident about our decision to reject or do not reject the null hypothesis. So if alpha would say be 0.01, that's really, really small. If it was 0.00001, then that's extremely small. So we are playing it extremely safe. We are really trying to avoid a type 1 error by having a super small alpha value. Now remember, if alpha, type 1 error, that's saying that we reject the null hypothesis when it's actually true. So if we're trying to minimize that probability of making that error, and if the error says that I reject it when it's true, that means we're not going to be rejecting it very often, right? We're going to be saying, I don't reject the null hypothesis. I don't really think there's anything different going on. I just think kind of the status quo, the normal things are taking place. So start to kind of think through what is alpha with this level of significance, how does this relate to type 1 errors, and how do we understand this idea of a small alpha value versus a slightly larger one. Okay, so when we compare these, either the p-value is going to be less or it's going to be greater than or equal to alpha. So if the p-value is less than alpha, we're going to reject the null hypothesis. We think that there is some significant difference between what the sample is versus what the larger population is. However, if the p-value is greater than or equal to alpha, we do not reject the null hypothesis. What this means is if we don't reject it, we don't have enough information to claim that there is a difference, right? There's almost always going to be a difference. Our sample mean, for instance, will never always be identical to the population mean. There's always going to be a difference, but the question is it significant enough? Are we convinced that it is going to be that crazy different than what our population was? So to build some intuition of why is it when the p-value is smaller do we reject the null hypothesis? So if we think about what this p-value is, this is the probability that we get a result that is as extreme or more extreme. So in this class, we're working with a lot of normal distributions. So let's say we have a normal distribution here. And always in the middle, remember we have this mean. So we have our mean in the middle. Our sample mean, let's say our sample mean is way out here. Right, so let's say this was our x bar. If our alternative hypothesis, so if our null hypothesis would say mu is equal to, I don't know, say 80, and the alternative hypothesis said that mu is larger than 80. So what if we are larger than 80? That's my alternative. That's what I'm wondering. That's the claim I'm testing. I'm much bigger than, say, this value of 80. So to be as extreme or more extreme, what that means is I am either out to this point, let's say, hypothetically speaking, this is going to be, say, 85, okay? To be as extreme or more extreme, I am going to fall within this range. More extreme means that I am larger than 80, right? So more extreme in this case, I'm going to be larger than my sample data. That's going to be my p-value. So my p-value over here is found by this. So if we're thinking that this is radically different than what my null hypothesis is stating, then I'm thinking that there is something going on, right? That I'm convinced, let's say if we talked about the medicine example, if we're saying that I'm really far away, I'm pretty convinced that the medicine might be doing something. So this, as the farther we go away, this p-value is going to be really, 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 really tiny, right? If we go all the way out to, say, 100, that's going to have such a small area out there at the end of this curve. We're pretty convinced that with a tiny p-value that we are going to be rejecting the null hypothesis, that there is something special going on here. And then also to understand kind of this as extreme or more extreme, when it's equal to 80, this is what it would look like. But if, let's say, the alternative hypothesis was, say, equal to 80, what that would mean is that if we are as extreme or more extreme, well, maybe we were 5 above. Well, we could also be as extreme if we were 5 below in that other direction. And so our p-value would actually be all of this. So we would have a combined area of p-value. So just as note vocab that usually gets thrown out, this would be an example of a two-tailed test, as opposed to the first example when we're just looking at one end of it. That would be an example of a one-tailed test. So you might see those words come across as you progress in your statistical career. You might see one-tailed test versus two-tailed test. All that is based off of, oops, this is not equals. All of this is based off of is our alternative hypothesis. If it's not equal, two-tailed test. If it was just larger or less than, it will be a one-tailed test.